Okay, so you should have watched the video for the end of blood and blood vessels. Sorry, blood vessels and blood. And if you walked in thinking you were going to have a test today, I have Bigfoot skeleton and the Loch Ness Monster's flippers that I'd like to sell you too. I don't know who started that rumor that there was a test today, but the syllabus does not say there was a test today. And have I ever moved something forward in time? Would that seem fair to you? That would be dumb. So if I ever move anything, it's always backwards. And where do you check to see if something got moved? Ilios. Look at the folder on the outside of the folder. Okay, back to this. So now we're talking about respiratory system. There are 4 steps in respiration. And of course it's steps, so you want to know these. We're going to go through them in detail, but the first thing you have to imagine is that you're a little tiny air bubble. And how are you going to get through this person's body, and how are you going to get to the tissues? So the first thing you have to do is you have to get from the outside environment, out here, into the body somehow. So the first step is exchange between the external environment and the internal. Of course, this person's breathing you in. So far it hasn't done diddly squat for them to bring your oxygen in, or you in as oxygen. So you brought it from the outside atmosphere into the lungs. You could respirate a dead person. You could ventilate a dead person. You could take and push on their chest and push air in out of their lungs. Is it doing them any good though? None. So the first step is technically called ventilation, putting the air in and out. The next one is exchange between the lungs and the blood. So you have to get it across that little membrane. What's the name of that cell that brings oxygen in from the lungs and pushes it into the blood? Starts with an A. The alveoli. So the alveoli, they take the oxygen from the lungs and they transport it over. I shouldn't even say transport. They help shuttle it over. How thick is an alveoli? Is it a columnar cell, a cuboidal cell, or a squamous cell? It's squamish, which tells you it's really squashed and flat. How many layers thick is an alveoli? 1. It's super, super thin. Right next to it's a blood vessel. The outer layer of a blood vessel, the endothelial cells, 1 cell thick, squamous also. So you have these 2 cells that are sitting right next to each other. Why would you want something so thin? Faster diffusion across the membranes, right? So you get back and forth. That's the next step, is getting into the blood. So you got the oxygen into the lungs, now you're getting into the blood. The third step is to transport it. What's the name of the transport molecule? Nobody wants to shoot for this. What transports oxygen through your blood? Red blood cell, what's the little transport molecule called? Hemoglobin, right? So hemoglobin takes it and carries it. A little tiny protein, technically. What's the thing in the middle of the hemoglobin that oxygen binds to? What metal is that? Iron. So it binds the iron in the hemoglobin, it's in the blood, and it's transported to whatever tissue you're looking at. It doesn't matter if we talk about a muscle, or we talk about the liver, or the kidneys, or whatever. Every tissue in your body needs to get oxygen. So it's transported to the tissue. The next step is getting it into the tissue. So it has to go back across that red blood cell, that blood vessel wall, the capillary, in through the interstitial space and into the cell itself. There's no transporter that goes across the cell wall for oxygen. Why? Because oxygen is small. It's what kind of polarity? Non-polar. And how does oxygen always move? High to low. So it's high concentration here in the blood. It's low concentration inside the cell. That's kind of goofed up. There's HTP should be ATP, and HO2 should be H2O. It's crazy. This is a slide from the book. So anyway, oxygen goes down to its lower concentration. It's turned into ATP, water, and carbon dioxide. Now you're accumulating carbon dioxide. What's going to happen here? You have lots of carbon dioxide. It goes from high concentration of carbon dioxide to low CO2 in the blood until it's at equilibrium, carried all the way back up into the heart, to the lungs. CO2's kicked out, and then it's breathed out again. It's a 4-step process that we're going to break down. So when we look at the lungs, we're going to talk about that process over and over and over again. But there are other things that the lungs do besides just move oxygen into your body and CO2 out. So they help move water back and forth. So when you breathe out, and you know this, especially on a day like today, when you breathe out, what do you see? Water loss, right? When dogs get hot, what do? They pant like crazy to try and get rid of that hot water, blow it out. So getting rid of water loss and heat elimination. Enhanced venous return. Every time that you breathe, and this is kind of a cool one that I never thought about until I took a physiology class, was every time you breathe, you actually pump blood. You go, your lungs expand, your lungs are compressed by the rib cage, so they can't go any further than the rib cage. They start compressing on everything else in this area. What's the other major structures inside this area? Your heart and what's that big, massive, those tubes that run through there? No, trachea's up here, down here. Blood vessels, right? The vena cava. Every time that you breathe, your lungs actually compress the vena cava. Does it push the blood backwards down into your legs? Why? Why does it not push backwards? Valves, right? So the valves won't let it go backwards, so the only place left to go is into the heart. Every time you breathe, by moving your lungs, you're actually pumping blood. So venous return. And of course, you already know the more blood you pump into the heart, the more you have to pump out. And number 3, contributes to the maintenance of normal acid-base balance. This one deserves a star. Forever, the first thing that you want to think about when you think of CO2, after CO2, is acid. Not necessarily oxygen, but acid. Everywhere you see a rise of CO2 in the body, you see a rise of acid. Every time you see a drop in CO2 in the body, you see a drop in acid. You don't always see the opposite happen with oxygen. So you may have a rise of CO2 in a part of the body, but also a rise in oxygen. You might see a lowering of CO2, but also a lowering of oxygen. But when you see CO2, you always can coordinate hydrogen ions, H+ with it. And I think I mentioned this the first day of class. If you start blowing out really quick, blowing up a balloon, you start getting lightheaded. Why? Is it the oxygen in your body? It's the CO2 in your body. What about the CO2? Lots of it or very little of it? You're blowing out really hard into balloons. What are you blowing a lot of out? CO2. And every time you breathe in, you take a lot of fresh oxygen in. You're bringing lots of oxygen in your body, but you're blowing too much CO2 out. So what state, based on what I just told you, what state do you start falling into? An acidic state in your blood or an alkaline state in your blood? Well, if you always associate CO2 with acid, if you're blowing out lots of CO2, what else are you losing lots of? Acid. So what state do you go into? An alkaline state, right? And that's what gives that tingly sensation. When you blow up a lot of balloons, you don't actually feel like you're going to pass out. You feel like a buzz. You know what I'm talking about? Kind of like, have you ever blown so hard that you start seeing stars? You actually start hallucinating? It's your neurons going psycho. They're going nuts. They're not turning off. They're going over crazy. And it's because of the alkaline state in your brain. I mean, if I ever got buzzed, that's what I would know or say. Number 4, enable speech, singing, other vocalization. You already knew this, so other than oxygen exchange, it's also for making sounds. Number 5, defend against inhaled foreign material. What are the little cells in your lungs that eat other cells? Macrophage. Yeah, so you have macrophage in there. And another cool thing about the way that your airway is designed, and I'll show you in a second, is that it's branched over and over and over again. There's a fork after a fork after a fork after a fork in the road. So that these bacteria or viruses that are flying through the air, they have a high likelihood of actually hitting the walls of your airway before they get to your lungs. And I'll show you what that means in a few slides. And number 6, remove, modify, activate, or inactivate different materials. Like, for instance, the lungs actually have a huge impact on blood pressure because they activate a chemical in your body called angiotensin, which you put an underline on or star next to like a week ago, maybe a week and a half ago. Angiotensin is actually activated in the lungs. So those are other things other than oxygen and CO2 exchange. Here's the anatomy. Like I said, every time I start a new section, I'll go through the anatomy again. When you look at the respiratory passageways, you have the nasal nares going in the nasal conch. The nasal conch is kind of like this bulgy structure inside your nasal cavity. Why would you want air going up over this stuff before it goes down into your lungs? What's the benefit of these things? They're warming the air, right? So they're warming the air before they get down and into your lungs. When you breathe, especially out in the wintertime, the air out there is really, really dry. Water works based on diffusion, even like humid water. It goes from where your blood's nice and warm or your airway's nice and warm and wet, and it will pull all the moisture out. If you breathe in that dry air, it's going to help crack your lungs. It's going to crack your lungs, and it's not a good thing. So you have the nasal concha that warms the airway. Breathing all the way down, you go through the pharynx, down into the larynx, down into the trachea, and as you're going down through the trachea, you start branching. So you split, or bifurcate. You split this in half, and then you split that in half, and split that in half, and split that in half, and keep splitting in half all the way down until you get these little alveoli structures. If you were a virus or a bacteria, they don't have steering wheels. When they are breathed in, they come flying through here, and hopefully they go in a straight path and they slam into this wall. The mucus on this wall is going to gather it up. The cilia is going to help bring it back up to your nose, and then you can pick it later. If it keeps branching, hopefully every time it comes to an intersection, it has a better chance of hitting that intersection, so you don't breathe that bacteria all the way down in your lungs. That's why you can be around with somebody that has the flu and not necessarily get the flu, is because you could breathe those particles in, but they get stuck in your airway and brought back up. So that, well, either you pick them later or you swallow them. So think about that the next time. Why would you swallow them? What would be the advantage there? Swallowing takes them down the esophagus and into the acids of the stomach to destroy it. Right. So there's the pathway. And I like this because the bronchiole sounds like a blood vessel that you just learned about last week. Arterioles. What did we call the arterioles? They were the what vessels? I gave you a nickname for every type of blood vessel. I said the arteries were pressure reservoirs. I said the arterioles were resistance vessels. They're the ones that control the size of the blood vessels, determine the blood flow into different organs. The bronchioles are the same way. They're the major resistance vessels. So if somebody has bronchitis or inflammation of these, it severely constricts the passageway. If somebody has, what's that disorder where if you breathe in certain types of allergens, it makes your airway start collapsing? Starts with an A. Asthma affects the bronchioles. It changes the size of those bronchioles really fast because they have what kind of muscle around them? Skeletal, smooth, or cardiac. Can people with asthma voluntarily control the size of their airway? So it has to be involuntary. So what would it be? Smooth, because the only other involuntary is cardiac, and that's only in the heart, right? So it has to be these involuntary smooth muscles. The bronchioles are just like the arterioles, except they carry air instead of blood. All the concepts you learned about in the arterioles, like that flow equals pressure divided by resistance, comes to play at the bronchioles again. And then the alveoli are kind of like the capillaries. What happens at the capillaries? They're the sites of exchange, and the alveoli are exactly the same. They're designed the same. They're simple squamous cells, really thin for fast diffusion. And then there's just a picture of all of those structures put together. You can see the branching. A term that you should get used to is a lot of times when they refer to the lung, they're referring to the batch of alveoli. Or if they talk about alveoli, they're referring to the entire lung's massive substance. Your book doesn't point that out, but it uses those terms interchangeably. When they say the lung, they mean all the groups of the alveoli together. Because the bulk of the substance in the lung is alveoli. Right, so there are your bronchioles, and you can see the bronchioles are wrapped in smooth muscle. They can be changed in size quickly. And it's the same principle. If you take the radius and shrink it in half, what did you actually do to the resistance? Yep, so if you decrease the radius, you did what to the resistance? Increased it. If you decreased the radius by half, what did you do to the resistance? You increased it by 16 times. So what did you do to the flow? You reduced it by 16 times. It's exactly the same concept, so you don't have to relearn all this stuff. You already know it. I'm a huge fan of saving brain space, right? So if you can take one concept and apply it across the board in different places, go for it. Same concept, you're just moving air instead of blood this time. And then you can see all the little alveoli are like grape-like structures. And you see the alveoli clusters are all stuck together. They have these little tiny pores that go from one to the next alveoli. It's almost like air has an escape route. So it comes down the tubes, the bronchioles, into the alveoli, and then it can actually circulate between the alveoli. So if this alveoli gets plugged, it can circulate air sideways. It doesn't have to go straight into the bronchiole. It can go from alveoli to alveoli, which is a big benefit because if something happens, like you get extra mucus here plugging it up, that alveoli doesn't collapse, it doesn't die, it just moves its air sideways. And then around the alveoli, you can see all these capillaries all over the place. If you don't have a capillary bed on a set of alveoli, the alveoli is actually worthless. Right, and this comes out a little bit blurry, but here you can see the inside hollow opening of the alveoli. The alveoli is going to take the oxygen, move it into the blood, and shuttle it away. There's not a lot of space to go across. Here you see that flat alveoli. There's a nuclei, there's a nuclei. So you see them holding hands, basically forming the wall of this alveoli. And then here's the blood vessel. There's a nuclei, so there are two cells. They're simple squamous. Quick, easy, fast diffusion. Right? You need to know these cells. So 3 types of cells make up the alveoli. The type 1 cells form the walls of the alveoli. They're just like endothelial cells. They lock into each other and they basically touch hands. They don't overlap like shingles. They're like shingles butted against each other. And they form, instead of forming round tubes, they actually form these sphere-like balls with little openings for air to go in and out to the bronchioles or to the lateral alveoli. And that's a type 1. They form the walls of the alveoli. Type 2 release something called surfactant. S-U-R-F-A-C-T-A-N-T. Surfactant. Surfactant reduces surface tension. That's all you really need to know right now. It just reduces surface tension. Surface tension wants to collapse your lungs. So surfactant keeps your lungs open. Surfactant doesn't get made until you're about 2 weeks before being born. And then your surfactant, these type 2 cells start getting active. And then as you're being born, they're stimulated by a chemical called cortisol to start producing. Why would they start cranking out right before you're born? Because the first time ever you're going to take a breath, and if your lungs aren't full of surfactant, you can't expand your lungs. That's why premature babies have a problem breathing, is because they haven't been able to make their own surfactant very efficiently yet. So they can give them artificial surfactant, yeah. And then macrophages, of course you know what these do. Macrophage, their name means to, eat big things. These are called alveolar macrophages. They're tissue specific. They get into the alveoli and they stay there. They don't move back and forth. Once they're in the alveoli, they're committed to staying in the alveoli. They eat bacteria, they eat viruses, they'll eat anything that gets in there. I used to have a little picture, I use it for another class, but I had a picture of a macrophage eating a piece of asbestos. It's crazy. It wants to attack the asbestos, but the asbestos can't be broken down, so it looks like this long javelin or double-sided spear. And the macrophage tries to eat it, and it just pierces straight through the macrophage and kills it. You can't get rid of asbestos once it gets in your lungs. So something like that doesn't break down easily, the macrophage is destroyed, and then the other cells just put a wall around it, slowly blocking off your lungs so that nothing gets in there. Here's an image. Here you see the outer wall. So what type of cell would that outer wall be? It's a type 1. Yep. And then you see the nucleus. And then here's one of the macrophage coming around looking for viruses, bacteria, dust, anything that shouldn't be in the lungs. And then there's a type 2 making what? What's this goo? Surfactant. Yep. And it reduces surface tension. And then there you can see the capillary wall. So it's a really short distance from the alveoli into the capillary. Right. So surfactant's made in which cell population and what's its function or purpose? Surfactant's made in which cell population and what's its function? Well, first of all, what type of cell makes surfactant? Type 2, so you know it has to be number 3 or number 4, and then what's the purpose? Decrease surface tension, right. It decreases surface tension. So number 3 is our correct answer. Right, next, so the lungs occupy most of the thoracic cavity. Remember, the thoracic cavity's primary 2 organs are the lungs and the heart. What's the third organ besides blood vessels that's in there? Anybody know? It's a gland that sits actually right in front of the heart and behind the sternum. And it gets bigger and bigger until you're 25 years of age, and then it starts shrinking and getting replaced with fat. Yes, the thymus gland. So the thymus gland is in there too. But the lungs take up the bulk of the space. Right? So 2 lungs, they have branching airways, and then there's this huge mass of alveoli. In between, everywhere you have alveoli, you have to have blood vessels. So you have the pulmonary vasculature too, picking up oxygen, dropping off CO2, and also bringing good things like nutrients to the lungs, because the lungs just exchange oxygen back and forth. They don't suck in. Hopefully you're not inhaling glucose unless you're snorting powdered sugar or something. But they have to get nutrients too, so you actually have circulation going over to feed the lungs and keep them alive. And then here's kind of the key here with number 4, lots and lots of elastic connective tissue. What's that give it the ability to do? Snap back, right? What's the word for stretchability? When I said that something's really, really stretchy, C word, it's very compliant, right? When I said it snapped back, I said it was very elastic, and I gave you the example of your underwear waistband. They're elastic, and their elastic properties start wearing down, but their compliance will stay good until the day you throw them in the trash, if you ever throw them in the trash. Sorry, it's a guy thing. And then the only muscle in the lungs, smooth. That's it. Here's a trick. When you breathe, is that a voluntary or involuntary muscle that's moving to breathe? It's a voluntary muscle, which means, is it smooth muscle that causes you to breathe? No, it's not. It's skeletal muscle. But that skeletal muscle is not in the lungs. Guess where the skeletal muscle that makes you breathe is at? The diaphragm, or, I shouldn't even say or, and, the diaphragm and, what's the name for the muscles between the ribs? Intercostals. Yep. So we'll talk about those later. What's interesting is the muscles that make you breathe are not in the lungs. They're actually around the outside of the lungs, and they just hold on to the edge of the lungs and pull them. That's all they do. They're not actually in the lungs. So the only muscle in the lungs themselves is the smooth muscle that goes around the arterioles and the bronchioles. Just like when we were talking about the pericardial sac, it's a sac that goes around the heart with pericardial. You have the pleural sac, which is the sac that goes around the lungs. It's exactly the same design. I don't know if I put the picture back up here again. Cool, I did. So I'll go back to the last one in a second, but imagine the lungs. Like you have this, I always use the fist in my analogies, but if you have a fist and you push it into a balloon, the balloon just wraps around the fist. The same thing if you have this lollipop and you push it in the balloon, it just wraps around the lollipop. That's what the pericardial sac and the pleural sacs do. They just wrap around the organ. When we talk about pericardial, what do we say the name of the membrane that touches the organ was called? The visceral, exactly. So you have a visceral layer, just like we talked about before, that actually touches the lung. And what's the name of the layer that doesn't touch the lung or the organ? Parietal. So you can see the sac, bless you, the sac goes all the way along, up and around, doesn't pop, it just wraps back around. So the airway, the tubes, the bronchioles and the bronchi just come into that sac and inflate the lungs. What I think is so cool about the lungs is that, remember how the skeletal muscle moves the lungs? The skeletal muscle doesn't technically touch the lung, it touches the sac. It pulls on pieces of the sac to expand the lungs. So the skeletal muscle never actually touches the alveoli or alveolar walls. And I'll go into that in better detail in just a little bit. Alright, so anyway, the two layers, you have the parietal pleura, which lines the inside of the rib cage, and you have the visceral pleura, which actually makes contact with the lungs. The cavity inside is called the pleural cavity, and it's full of something called intrapleural fluid, which means within the pleural fluid. Why would it be fluid? Why would it not be air? What do you think the benefit of having that as fluid would be? One thing is that, how often do you breathe? Yeah, hopefully like every couple seconds you're taking a fresh breath. So you're constantly breathing. It's the same idea with the heart where you're reducing friction. So it reduces friction for one thing. If you get friction and you get inflammation, it's called pleurisy. There's another name for this, and it's called inflammation. Pleuritis. Yep. And again, just like with pericarditis, it sounds like two pieces of leather rubbing against each other. So I think I told you about my weekends in the Harley bar, right? Okay. That sound. Same sound. It's very similar material. Just have them hold their breath, and if that sound keeps going, then you know it's the heart. If it stops, you know it was the lungs. Okay, this definitely gets a star. So now we're going to talk about respiratory mechanics, or how breathing works. It seems like such a simple concept because you do it without having to think about it, but it's actually really complex. It's interesting. So there are 3 pressures that you have to know to understand this. First is the atmospheric pressure. You can write 760 mm, capital H, little g. And that stands for millimeters of, what's Hg? It's mercury's chemical symbol. 760 millimeters of mercury. The average atmospheric pressure where we're at about sea level is 760 millimeters of mercury. That's the air pushing in. You can't see air, but there are trillions and trillions of air molecules stacked above your head, and all of that weight of all those air molecules are pushing down and into your lungs with a pressure of about 760 millimeters of mercury. If you go up into the Rocky Mountains or you go up at the peak of Mount Everest, they're a lot less. So the pressure pushing air into your lungs is a lot less when we just say that there's a lot less air up there. And then number 2, intra-alveolar. Where would that be at? Look at the name. Within the alveoli. That's inside the hollow sac of the alveoli. That's the space inside of there. That one's constantly changing. Your atmospheric pressure doesn't change that much. If you have a massive storm roll through, the pressure changes a little bit, but it takes a lot to change that pressure. The intra-alveolar changes quickly. In fact, you change it just to take a breath. And the last one is the intrapleural pressure. Where would that be? Within that sac. So the intrapleural pressure is actually a water pressure. It shouldn't have air in there. One of the other things about this being water is that water's hard to squeeze. It's really hard to squeeze water or to stretch water. It just doesn't do either of those very much. So if I pull on one side of this, if I reach down here and I pull, like on the diaphragm, I pull on this part of the sac, all these water particles hold hands. They don't stretch out, so what are they going to do to this other side of the sac? They're going to pull it with, right? You pull on this side of the sac and it pulls the other side of the sac with it. It would be like holding a water balloon in your hand and taking that little part where you put the water in and pulling it. If you pull on it like this, you'll notice the other side caves in. It comes with it. Water doesn't stretch very easily. It doesn't compress very easily either. So what you do with that water affects both sides of the sac equally. You have to have a pressure in there that creates a suction so that the water is already in the sucking position. And I'll show you that in better detail. Right, so here are the 3 pressures. Out here, and over, we're going to draw this to represent the lungs. So this is one alveoli, but just assume that it represents all of the alveoli in your lungs anytime you see it. So the first thing, the atmospheric pressure outside your nose, around you, pushing down on your head, everything, 760 millimeters of mercury. In here, in this blue watery space, is always less than that. That's all you have to know. You don't have to write down 756, it doesn't matter. All you have to know is that it's always less than atmospheric pressure. It has to be. And we'll talk later about if you pop this wall in atmospheric pressure and this intrapleural pressure equilibrate, if they become the same, you've got problems. Anybody know what that is when you have a quote-unquote collapsed lung? There's a P word for it, huh? A pneumothorax. Yeah, so if you pop this sac, you have something called a pneumothorax. It's bad news. And then the third one is the intraalveolar, and that's the pressure in here. And the intraalveolar, you can see there's nothing stopping or disconnecting it from the atmospheric. So as you change this one, it's going to keep trying to equilibrate with the atmospheric pressure. If I squeeze on this, it's going to raise the pressure here, and trust your gut on this. If you have high pressure inside the alveoli and lower pressure in the atmosphere, where's the air want to go? If it's high pressure in the alveoli and low pressure outside of the alveoli or outside your body, where's it want to go? Out. If I pull on this wall and I create a low pressure in here, so it's low pressure here, high pressure outside your body, where's the air want to go? In. It's the same laws with diffusion. It's kind of one of those universal laws, like I said back when we talked about diffusion. Things just want to go from high to low. Even pressure does that. So for you to breathe, all you're doing is you're changing the pressure in this space and allowing air to move based on its pressure gradient. Like I said, it's a super simple concept, but it's tricky if you overthink it. Here's millimeter of mercury. This is how they test it. So they put this whole chamber in a vacuum. They have this little jar, this beaker that's full of mercury at room temperature, it's liquid. Did anybody ever play with mercury when you were a kid? Right, you're not supposed to. When I was a kid, they didn't tell it was bad, so I remember breaking a thermometer open and actually holding mercury in my hand. But I'm fine. Actually, it's mercury getting in your system. They came with the name Mad Hatter. If you didn't know that, look it up sometime. Because it'll go into your brain and makes you crazy. I'll leave that alone. Me and the whole mercury story. So anyway, what they do is they put this in a vacuum where there's no air around it. No oxygen molecules at all. There's no carbon dioxide, no anything. It's a vacuum. Not like a vacuum cleaner, but a vacuum with no air. Like outer space. And then what they do is they put this test tube, like cylinder, upside down in here. And then what they do is they let air come in. And all the air around will come in. It'll push down on the mercury, and it will push the mercury up. How far up that tube? 760 millimeters up that tube. And that's where they came up with the 760 millimeters of mercury. Because the air pressure, wherever you're at, will push down that liquid and force it up the tube. How far it forces it up the tube depends on the atmospheric pressure. That won't be on a test, but if you ever wonder where it's coming from, then it helps explain it. So if you took this tube to, let's say, the bottom of the ocean, and you let all of the water molecules push down on the mercury, what would happen? Do you think it would go lower or higher? What do you know about the pressure deep down underwater? It gets higher, so it would force this further up the tube. What if you went up at the top of Mount Everest and you opened this vacuum? It would be lower on the tube because there's not much air pushing it up the tube. There's not much air forcing it up. Okay. And then these different pressures you can see, and I already talked about this. I kind of went with your gut instinct to help explain this. But as soon as you expose the inside of the alveoli to the atmospheric pressure, so by the way, the only way to block off atmospheric pressure from the alveoli is to close your mouth and plug your nose at the same time, so nothing exchanges back and forth. Oh, I hate doing that. I can't believe I just did that to myself, squeezing your nose. But anyway, it's going to try and hit equilibrium. What do you know about this blue liquid? It should always be lower pressure than the atmospheric pressure. So this will always stay lower. It will always stay, well, typically it will stay lower than this pressure too. But it always has to stay lower than atmospheric pressure. It creates a kind of suction to help your lungs from collapsing or prevent them from collapsing. Next, the lungs follow the movement of the chest wall for two reasons. This also deserves a star. So the first one is something called intrapleural fluid surface tension. Surface tension is just a fancy way of saying that water molecules like to hold on to each other. They're like little tiny magnets. You already knew they have kind of a north pole and a south pole. When you put them next to each other, they go pink and they stick together. You can see this on a big scale if you go out in the summertime and you wax your car, lots and lots of wax, and then you take a mist of water and you spray it over the car. So it's just a mist. Little tiny droplets that you can't really see the droplets, but you see the fog they create. As soon as they hit the car, what do they start doing? Right, it's a frictionless surface now, so those magnets can pull to each other. It's like putting two magnets close enough together and letting go. They go and they stick together. That's called surface tension. If you put them across the surface, if you spray them across the surface of your skin and you have oily skin, they do the same thing. They stick together. If you put that fog inside of your lungs, microscopic alveoli with all those little microscopic water particles, now imagine this on a bigger scale. Those little tiny particles are real close to each other. They're going to start pulling. They grab the wall of your lung and they start pulling the walls of your lung together. What are they trying to do to your lungs? Those little water particles and their surface tension are trying to do what to your lungs? They're trying to collapse it. They're trying to pull the walls of the lung shut. So those water particles pulling together is called cohesiveness. It's the same thing with all the dense water that's inside that pleural cavity. They're all holding together by this magnetic force. If you pull on one side, they're like a long chain of magnets. They pull with each other. Right, and then the next one is a transmural pressure gradient. Anybody know what a mural is? Don't imagine the body. Imagine that you walk into a museum. What's a mural? It's a thing they hang on the wall, right? Or paint on the wall. So a mural is basically a wall. What would transmural be then? Across the wall. It's telling you the gradient or the pressure across the wall. So If you start increasing the pressure on one side of the wall over this side, it's going to push towards the lower pressure. But you have two walls, and this is the interesting thing about the two walls, is that these two walls' pressures are actually pushing in opposite directions. One of those pressures is across the wall of the lung. Across the wall of the lung is trying to collapse your lung. It's trying to pull your lung shut. The other one is across the thoracic wall. That one's trying to expand your lung. It's trying to open your lungs up as completely as you possibly can. They're in two totally different directions, so they're actually opposing each other. They're pulling against each other, like this. So here's the wall, right? Here's the first wall, the inside of the lung versus the water. This one's trying to pull shut. It's pulling inward. The other one's out here by the rib cage, pulling outward. Again, and I'll say this a bunch of times because remember, this alveoli represents your whole lung. This side would be connected to the ribs. This side would be the empty hollow space inside where the air is going. You have one force trying to pull in. You have another force trying to pull out. And what they're doing is they're just tugging on each other, like a tug of war. The little water molecules are the magnetic rope that they're pulling on. So those pressures. And then here's the big picture. Whoops. Sorry. Remember, neither the lungs nor the thoracic wall are actually in their natural position. They're always trying to oppose each other. So they're moving against each other. The only way that you would find out where their natural position was is if you took a knife and pushed it in through your ribcage and punctured that wall. If you've ever seen somebody with a collapsed lung, does their chest look sunken in? Their chest actually is expanded out. It's way out, but if you took an x-ray of them, guess what happened to their lung? It shrunk down. Their chest wall went to its natural position, which is out here. Their lung went down into its natural position, which is shriveled up. They lost their opposition. Those two forces holding together by that water sac are really important. You puncture the sac, you lose that tension. So if I were to ask you a question like this, why do the lungs follow the chest wall? Put 30 seconds on the clock. Okay, which one? What about number one? Intrapleural fluid tension and the transmural pressure gradients. A lot of people that agree with that. How about number two? A decrease in surface tension between the parietal and visceral pleura and transmural gradients. More people said true to the first one. Nobody even said anything to number two. How about number three? Air in the pleural cavity acts as a suction to hold the parietal and visceral pleura together. Nobody wants to say anything about that. Looks like number one. Well, what's wrong with number three right away? Hopefully there's no air in the pleural cavity. What should be in the pleural cavity? Should be water, right. So if you flip back or look in your notes, ding, ding, oops, wrong way. It was right here. Intrapleural fluid tension and the transmural pressure gradients. This is the way tests are. If you didn't catch that on the first test, everything comes from the notes. Everything on the test comes from the notes. Where should you study? Homework or notes? Notes. Where should you study? Open the book or look at the notes? Notes. If you need more detail to understand something, open the book. If you want to know some details you might need to know for other classes down the road, look at the homework. If there's something you'll definitely need to know moving on beyond this, whether you get into clinicals or whatever, look at the notes. The notes are the points that you need to take on beyond this class. And this, you think you're ever going to have to hear about something called a pneumothorax ever again? Yeah, it's one of the primary things you have to worry about with respiratory disorders. Asthma, pneumothorax, emphysema, bronchitis, those are the biggies. Right, so while we're talking about pneumothorax, there it is. So it happens if you puncture the thoracic wall or if you have a hole in the lung. Let me show you. So you can puncture from the outside. If there were a gunshot coming in from the outside, a knife wound that just barely went through the rib cage and just punctured that sac, but didn't make it all the way into the lung, that would still do it. You don't have to go all the way into the lung itself. You just have to puncture the pleural cavity to get a pneumothorax. The other way to do it is if it's something from the inside going out. So let's say that there's a bacteria or something that's destroying the inside of your lung and it punctures a hole in that wall. Then it came from the inside out. If you're a firefighter and you run into a fire and you want to be a hero and you pull off your mask to give it to a little kid and you breathe in the hot air, what could you have just done? You could have just dried out the inside of your lung and cracked the inside, and now you gave yourself a pneumothorax. So it's any way that you puncture this wall, suddenly 760 out here, what do you know these forces want to do? Everything wants to go from high to low until it hits equilibrium. At the point where you've hit equilibrium, there's no more suction anymore. So if this is 760 and this is 760 and that's 760, there's no pressure gradient anymore. You could keep pulling. In fact, people with a pneumothorax, you'll see them and they're going, and they're using the muscles in their neck, they're using their rib cage, and the rib cage is way out, like they're getting big, deep breaths. They can move this lung, or this chest wall, but they can't move the lung on the inside. So they're still struggling for breath, and it doesn't matter how far they pull that chest wall out, the lung inside is just collapsed in there. So then they have to stick a tube in here, and they create a pressure gradient. Sometimes they'll suck the water out. Sometimes they'll just create like a valve there, so that they do it on their own, and they move their own fluid out. We'll actually look at pneumothorax for the next case studies in lab. Okay, oops, I'll go back to that slide again. So pneumothorax, if the atmospheric pressure becomes the same as intrapleural, or if the intrapleural pressure becomes the same as alveolar. The moral of the story here is that you always want the intrapleural pressure to be lower than either of these other two. You always want them to be lower than the atmospheric or the alveolar. And in most of the pictures it keeps saying 756, 756 over and over and over again. The point is that it should always be lower than the atmospheric or lower than the intraalveolar.
Why is pneumothorax common in males that are young that grow faster?
Just think of stretching something faster than it should be. If you have a balloon that you overstretch too fast, what could happen to it? Snap, pop, yeah. In fact, you usually see that real thin weak point. That's where it's going to give at, and that would be the same thing. And once you have one, you have a high likelihood. Yeah, it's like a 50% chance of recurrence in the next year or year and a half or something like that. Okay, so some rules. These are big picture rules, and I kind of think I'm beating some of these to death, but intraalveolar pressure must be less than the atmospheric pressure for air to flow into the lungs during inspiration. So in other words, intraalveolar is that hollow airway inside the alveoli, not the water sac, it's the hollow airway. Atmospheric pressure is outside, and your common sense is telling you again, if the air outside is high pressure and the air in your lung is low pressure, where's the air naturally want to go? High pressure outside, low pressure inside. What's your gut tell you? It wants to go in. What's that process called? Inspiration. You breathe in. I use the muscles in my chest to create a low pressure inside my lungs, and it just naturally sucks the air in. Next, intraalveolar pressure must be greater than atmospheric pressure for air to flow out of the lungs. So this time, I'm going to take my lungs, all the muscles around my lungs, I'm going to squeeze the lungs. I create a high pressure inside the lungs. Now it's high pressure in the lungs, low pressure outside. Where does the air go? It goes out. What's that called? Expiration, or exhaling. So in other words, rule number 1 is telling you what has to happen for inhalation, and number 2 is for expiration. And the next one, the respiratory muscles that accompany breathing do not actually touch the lungs. They're not actually working directly on the lungs. They're working on what thing around the lungs? The pleural cavity. They're working on the pleural cavity. So they pull on the pleural cavity. When they pull on the pleural cavity actually changes the size of the lungs, which changes the pressure. So as you pull across that pleural cavity, you're going to pull across the transmural gradients. Remember? The lung wall, or chest wall, pulls on the water, pulls on the lung wall, and it expands the alveoli or the lungs. It's a step-by-step process. Boyle's Law, you're never going to have to do the math with this, but you need to know the concept. So Boyle's Law says that if you increase the volume, you decrease the pressure. If you double the volume, guess what you do to the pressure? Cut the pressure in half. If you cut the volume in half, guess what you do to the pressure? You double it. And again, some of these concepts, I like to anamorph them and make it more human. If this room we're in were one alveoli and you were all oxygen particles, and I took this wall and I shrunk this room in half, how would you feel? Less pressure or more pressure? More pressure. If I shrink the size of the room, there's more pressure on you. What do you want to do? You want to leave, right? What if I take this room and I double it in size? How do you feel? Less pressure or more pressure? Less pressure. Do you want to be in the crowded room out there, or do you want to be in this big open spacey room in here? You want to be in this big open spacey room. So let's say I take this chamber and here are, I don't know, 15, 20 molecules in here. So there are 20 molecules, and I have, let's say, 1 liter is my volume. And I take and suddenly I compress it to half the size. What happens to all these molecules? Do they feel more or less pressure? More pressure. If you shrink the size of something, you increase the pressure. Boyle's law just says it's proportionate. If you cut the volume in half, you double the pressure. If you take those same molecules and you pull this chamber open, you make more space for it. What do you do to the pressure on the inside? You make the volume bigger, you take the pressure off the molecules. So if you double the size of the container, you have half the pressure in it. Your lungs manipulate that with skeletal muscles. And here are the skeletal muscles you have to know. What's the big one across the bottom of the lungs that separates from the abdominal cavity? The diaphragm. Yep. Diaphragm is a big sheet that goes all the way around the bottom of the rib cage, connects to the vertebra. It only has a couple holes for food to go through, so the esophagus to go through, and also for the aorta and vena cava to go through. But otherwise, it's a sheet, one continuous sheet. When you contract that, does it push up or does it pull down? When you contract the diaphragm, does it push up or does it pull down? I'll give you a hint. Muscles never push. Ever. Ever, ever, ever do muscles ever push. Never. So they must do what? Pull down. When you take a muscle and you look at its endpoints, anytime you contract a muscle, it always shortens and it pulls. It doesn't matter if I push my arm out. What am I actually doing? I'm shortening my tricep, right? I'm contracting the tricep. I'm just shutting the bicep off and letting it work. Muscles always only pull. So when this muscle pulls, it shortens, pulls down, and it's connected to that pleural sac. So what's it actually do to the pleural sac? It elongates it, right? It stretches it down. What's it doing to the length of the lungs? Making the lungs longer, just like a syringe. When you pull back on a syringe, the plunger, it starts sucking things in. In this situation, you're sucking air in. You're increasing the volume in the lungs, decreasing the pressure in the lungs. So where's the air want to go? Does it want to go from the low pressure lungs to the high pressure atmosphere? It wants to go atmosphere down into the low pressure lungs. As you bring this diaphragm down, the air naturally starts shifting in and following it. Which intercostals do you think you use to expand your ribs? So not only are you taking the lungs and lengthening them down, you're making them more round too. Which intercostals do you think you use to expand the lungs? The internal or the externals? You're using the externals. You pull them up and out. It expands the lungs, decreasing the pressure and bringing air in. So you have two sets of muscles that cause you to inhale. You have to contract the diaphragm and you contract the external intercostals. Right, so we'll talk about the entire respiratory cycle from the beginning to end. So just like when we talked about the cardiac cycle, imagine you're at rest. Your lungs are at rest. So before inspiration, they're at rest. Your muscles are relaxed. There's no airflow. You hear nothing moving. At this point, your intra-alveolar pressure inside the hollow ball of the alveoli is exactly the same as the atmospheric pressure. They're called what when they're the same? They're at equilibrium. Does the air molecule want to move anywhere? No, it's happy. There's no movement of air right now. You're rested, completely relaxed. Then suddenly, you start contracting the diaphragm. Where's the diaphragm go? Push up or pull down? Pulls down. your external intercostals do what? They pull out. You're taking the lungs, you're lengthening them, and you're making them bigger around. What are you doing to the volume of the lungs? You're increasing the volume, which means you're automatically doing what to the pressure in the lungs? Decreasing it. So right away, you went from 760 if you just assign a volume, because remember, everything's at equilibrium, right? 760. Then you drop it. It doesn't matter if it's 759 or 757. It doesn't matter. As soon as you drop it from 760 to 759, in your lungs is 759. Outside is 760. What's the air want to do? Start moving into the lungs. Right away, it's going to start moving into the lungs to try and hit equilibrium again. So here are the technical parts. Inspiratory muscles, the diaphragm and the external intercostals, are stimulated to contract by the phrenic nerve and the intercostal nerve. I'll let you figure out which one controls which, but I'm going to tell you right now, if you haven't figured out intercostals and intercostals, woo, get some coffee. The phrenic nerve is really actually an important nerve. How many people here have had the wind knocked out of them? The wind wasn't actually knocked out of you. Nobody stole it from you, right? What happened is that you fell so hard that you shocked the phrenic nerve. It's a nerve that controls the skeletal muscles to help you breathe. When you shocked it, you can't contract the muscle that it was controlling before. Right? This is a skeletal muscle. The brain has to control it. If there's no signal going down to that diaphragm, you can't contract it. So, could you still move air when you had the wind knocked out of you? What were you doing? You're going, right? You're still moving the intercostals, but the diaphragm's just sitting there going, doing nothing. So you're moving a little bit of air, but it feels like you can't move any because the diaphragm's what normally pulls most of the air in. And if you've ever had that happen, I know you remember every detail of that moment, right? I remember I was playing Tarzan on a willow tree. Not good. And I remember I so vividly remember feeling the little leaves snapping between my fingers, and then those snap, snap, snap of the willow branches until I was laying flat on my back, and all the other kids were looking down at me going, oh my God, our parents are going to kill us if he dies, right? But what happened is you had the phrenic nerve shocked. You didn't have the wind knocked out of you. You paralyzed that nerve briefly until it came back. Just like making your leg fall asleep, it'll come back. It just takes a few seconds. And hopefully you live through those few seconds, right? It's the same thing if you do martial arts. They always tell you if you're taking a blow to the chest, what do? Stiffen your chest? They tell you let it go, relax. Because if that person hits you so hard it shocks the phrenic nerve, you look like a big wimp because you go, you got the wind knocked out of you, right? By that little kid that's this tall that just karate chopped you in the gut. All right, so anyway, when you fire these muscles, it enlarges the thoracic cavity. It lengthens the thoracic cavity and it brings it outwards, which dramatically decreases the pressure. The pressure starts dropping right away. As soon as the pressure hits 759, it doesn't matter how fast it drops. As soon as it hits 759, the air starts coming in. And it keeps rushing in and rushing in and rushing in until you're at the end of that inspiration. Now it's time to get it out. Right? So at the end of inspiration, now what you do is you shut off those nerves. You turn off the phrenic nerve, you turn off the intercostal nerve. As soon as you turn them off, what happens to those muscles? They relax. If they relax, they go back into their natural position. The elastic properties start bringing them back together. Which process is active? Breathing in or breathing out? Which one's active? In other words, which one requires energy? Breathing in. Yep. Expiration is totally passive. All you do is shut off your muscles, and they just collapse down into a natural position. So at the end of inspiration, the muscles relax. The cavity starts compressing. It gets smaller. So as soon as the chest cavity gets smaller, what happens to the pressure? Volume decreases, so pressure must increase. As soon as the pressure goes to 761, but out here it's only 760, where's the air go? Up and out. Right? That's expiration. All the way until you're completely done. And then there's that pause, and you start the whole cycle over again. At that pause at the end, air is equilibrated at 760 outside and inside, and you just go back to step one, over again. Those are the steps. You instinctively just do that. You don't have to think about it, but that's how it works. Right. And then here, again, you can see the diaphragm pulling down, the external intercostals pulling out, expanding your ribs. These are for just regular, normal breathing. If you want to forcefully exhale, then it becomes an active process. This is when you need to get air out fast, like coughing, blowing out candles. The older you get, the harder it gets, right? But when you're coughing, what muscles are you using? They're not the normal muscles, right? Because normally you just turn off muscles and you go, ah. Now you're doing what? You're contracting your, just blow out, blow into the hair of the person in front of you. What do you feel contracting? Your abdominals. And if you've had a cold lately and you're coughing all the time, when you're done with the cold, how do your abs feel? Sexy and ripped, right? It feels like you've been working them really hard for a week because you have. You've been working your abs more than you probably ever do when you're sick. So that's my goal, is that I'm not going to exercise again until I get a cold, which forces me to work my abs whether I like it or not. And then I'll start exercising. I haven't been sick in like 3 years, which tells you when the last time I exercised. And then the other set are the internal intercostals. Not the externals. The externals pull the rib cage up and out. The internals will actually collapse them. They take your ribs and they pull them closer together, compressing the lungs. When you're forcefully blowing out, are you contracting or moving the diaphragm? Are you actively contracting or moving the diaphragm? No. When you squeeze your abdominal muscles, you're compressing your guts, right? You're smashing the small intestine, the stomach, everything. And what's happening is all of your guts can only go in two directions. They either come out your ass or they go up in your lungs. When you squeeze, hopefully they're not pushing stuff out that end. They're pushing up. When they push up, they smash the lungs, compressing the lungs and blowing air out. There are two times that you really use this, two important times. One's when you're coughing, trying to get air out, or sneezing, coughing, sneezing. The other one's when you use what's called the Valsalva maneuver, and that's when you're in the bathroom and you're washing your hands in the stall. Somebody's going, ah, right? They're squeezing exactly the same things, they're just trying to push it out the other end. Just trying to make it real. Memorable. Real memorable. Okay, so here are the four types of breathing. You've got normal expiration, which is totally passive, no energy required. The last thing you'll ever do is expire, right? As you expire, you actually expire. No energy required. Inspiration is an active process. You use energy to contract the external intercostals and the diaphragm. Forced expiration is not the same as expiration. Forced expiration is when you're squeezing the abdominal muscles. You're squeezing the internal intercostals. You're trying to compress the lungs as hard as you possibly can and blow as much air out as you can. That requires a lot of energy. And then forced inspiration is not a normal breath. Here's a normal breath. You can't hear it. It's you sitting there just breathing without even thinking about it. You don't hear it. Hopefully your neighbors next to you don't have to listen to you breathing. But when you force inspiration, you go, and you breathe in, what muscles do you use now all of a sudden? You can feel it. If you watch somebody struggling for breath, look at their neck. It's like bulging, right? They're using the sternocleidomastoid, the SCM, trying to pull up on the clavicle, trying to pull up on the first ribs to try and get any extra space in the lungs they can. They're also using the scalenes to pull up on those ribs. So the extra breathing muscles for inspiration are the SCM and the scalenes. All of these are active except which one? Expiration. Just a normal expiration is passive. No energy required. Just let go. You just breathe out. So here's the process. If I want to inspire, I want to bring air in, what number do I need to change? Do I change the atmospheric, the intraalveolar, or the pleural? I change the intraalveolar. As soon as I change this to 759, what I know is automatically going to happen. Air is going to rush from 760, because I can't control the atmospheric air. It's going to rush from the 760 down and into the lungs. How can I change that number? What am I going to do to change it from 760 to 759? If I want to bring air in, what do I have to do to the volume in here? I increase the volume. What's it do to that pressure? It decreases the pressure, right? So the pressure goes to 759 because I increased the volume. The air starts racing in, sucking in, And now I have a full lung, right? Now what do? Relax the muscles out here. What are those muscles going to do? They're going to smash the alveoli. And as soon as I smash the alveoli, what do? I shrink its size, so what do I do to its pressure? I increase its pressure. Now it's at 761. What's it going to do? Blow up and out to 760 until both of these hit 760. And then I start the process over, right? I bring it back down to 759, suck air in. Take it up to 761, blow air out. So it's constantly, watch the intraalveolar. If the intraalveolar is lower than the atmosphere, air comes in. If it's higher than the atmosphere, air goes out. And you can watch the chest wall and the alveolar wall, they go right along with each other. There's a slight shift here, but they're always moving in parallel. As one goes down, as one pressure goes down, the other one goes with it. As one pressure goes up, the other one goes with it. This is kind of cool. Anybody know what this is? And if you already looked at the slides and you know, this is like a giant syringe, right? It's like a giant hypodermic needle. Except, instead of having a needle tip on the end, you actually put a person in there. Boop. So you put a person inside of here, you have a collar that seals around their neck, doesn't cut their blood supply off, but it creates a seal, an airtight seal around their neck. And then you start pulling on the plunger on this end. As you pull on the plunger, the pressure pulls up on their chest, which pulls on their chest wall, right? Expanding their chest wall, doing what to their lungs inside? Expanding the lungs with it. What happens to the pressure inside of their lungs if you expand them? It drops. Their nose is an atmosphere, right? The atmospheric pressure out here. The air races into their nose, down into their lungs, and then this little motor will compress that syringe, smashing their lungs. What's it going to do to their chest size? Shrink the chest, doing what to the pressure? Increasing the pressure, blowing it out their nose. What are you doing for them? Yeah, this was like the first artificial respirator. It was called an iron lung. It makes them breathe. Breathes in, breathes out. Okay, so which of the following is a step in the mechanics of breathing? So which one of those is a real step? How about number 1? True or false? Air flows into the lungs, causing the lungs to expand. Does the air just blow into the lungs, causing your lungs to puff up? No, it's the other way around. The lungs expand, pulling the air in. So number 1's not right. Number 2, thoracic cavity enlarges, causing the alveolar pressure to drop below the atmospheric pressure. That looks pretty true, right? Your thoracic cage gets bigger, the pressure drops in the lungs, and the air blows in. So it looks like number 2 is the right answer, but double check 3 and 4. The diaphragm pushes up into the thoracic cavity during inspiration, but down during expiration. It's false. In fact, does the diaphragm ever push? No. It pulls. It pulls down. It's like a rainbow, and when it contracts, whoop, it flattens out. So number 3 is wrong. Number 4, passive expiration requires contraction of the diaphragm. Number 1 is passive and contraction. What do you know about those two things? Passive means no energy, but when you contract a muscle, it requires energy. So it contradicts itself, right? So passive expiration requires contraction of the diaphragm. It's actually inspiration that requires contraction of the diaphragm. So number 2 is our right answer. Oh, look. It's an equation. Do you need to memorize this one? No, why? Because you already have it memorized. It's flow equals pressure divided by resistance. You've seen it before, and I told you it would be back. All you have to do is change it from blood flow to airflow. All the factors are exactly the same. So if I double the pressure, what do I do to the flow? I double the flow. If I double the resistance, what do I do to the flow? I cut the flow in half. It's exactly the same principles. If I look at radius, if I increase the radius, I'm just saying increase, I'm not giving a number. If I increase the radius, what do I do to resistance? If I make the radius bigger, resistance goes down. If resistance goes down, what happens to flow? Flow goes up. All the same principles we talked about when we talked about blood vessels. Nothing new. And we're going to talk about this in more detail when we talk about things like asthma. So you can see a nice open airway, normal healthy person, breathing in, breathing out, and then suddenly with asthma, it takes the radius of that airway and shrinks it down. What happens to the resistance in that person's airway? Resistance goes dramatically up. What happens to the airflow? Goes dramatically down. Does it have to be, what's another disorder that could cause this? Decreased size in the airway. Asthma takes a smooth muscle and constricts a smooth muscle. What else could you do to decrease the size of the airway? And 'tis the season, right? There's probably, I don't know if anybody here has this right now, but you probably know somebody right now that has this going on inside of them. Bronchitis, right? You have all this mucus on the inside. Your airway is an okay size, but it has so much mucus in it, it decreases the size of the airflow, or the airway. Same idea. It's the same concept. You learn that concept, and you've got several diseases taken care of. All right. I keep feeling like I say this is important, but you want to start by this one too. Regulation of airway resistance depends on the body's needs, and I talked about this today. I talked about the first day of class. Carbon dioxide is the primary determinant of breathing. It's not oxygen. It's carbon dioxide. Carbon dioxide levels in the brain tell the brain breathe more or breathe less. And it's actually not carbon dioxide. Technically, it's, guess what, other chemical that's always associated with carbon dioxide? Acid. It's the acid levels in the brain. And I'll talk about that in better detail. By the way, what part of the brain regulates your breathing, your life basic ability to breathe? The medulla oblongata. It measures the acid levels directly. If you have high CO2 in the medulla oblongata, you have high acid, and it says, holy crap, you need to start doing what? Breathe slower or breathe faster? If you have high CO2 in your brain, what should you instinctively do? Get more CO2 in or get rid of it? Get rid of it. What do you do to get rid of CO2? Breathe more. So somebody that has a lot of CO2 or high acid level in their brain, what physical sign will you know that that's happening? They're going, if you ever see somebody with diabetic ketone acidosis, does it have anything to do with their breathing? Was it their lungs' fault that they have acidosis? Right, it's not the lungs' fault, but does it matter? What sign are they going to be giving you? They're going, it's almost like they just walked up a flight of steps really quick, right? They're breathing heavy. They're deep breathing. Why? There's so much acid in their brain, they're trying to get rid of CO2 that takes the acid with it. So again, if you get the big picture, it makes so many things so much easier to remember. So regulation of airway resistance depends on the body's needs, CO2 levels. If you have high CO2, you dilate the airway. Why? If you have a lot of CO2 inside of you, why would you dilate the airway? To blow it out. If you have low CO2, you need CO2. Do you want to open up your airway and lose that valuable CO2? No, so what do you do to the airway? You constrict it down. It's an easy concept to understand, but for some reason it's hard for a lot of people to remember that because we automatically want to keep going back to it's oxygen that makes us breathe differently. If you want to test this, and I'm saying this like sarcastically, don't go home and do this. If you want to test how important oxygen is or how important oxygen makes you respond, if you see somebody that's in a carbon monoxide filled house, are they going, oh my God, I can't breathe? What are they doing? Like, God, it's been such a long, miserable day. I just want to take a nap. Just let me lay down in this nice, comfortable environment and take a nap. A dirt nap, right? Because it's not oxygen that controls the panic, it's CO2. But if you put them in a room with high CO2, guess what they start doing? Like, oh my God, I feel like I can't breathe. I just feel really anxious. I gotta get out of this place. They start feeling panicky and they want to leave. It's the CO2 that actually drives that, not oxygen. Right? And I made an enemy my very first semester teaching here because I said that. Did I tell you the first day about it? There was a nursing instructor that had apparently beat into their student brain, or I'm guessing it was a student that misunderstood, but I told that story about the balloons, and a student actually said, that's not true. My nursing instructor says it's because of oxygen. I said, your nursing instructor is way wrong. Not a good thing to say. So I don't know who it was, but I turned somebody against me that day. It was most likely the student misunderstood it. It's CO2 that drives breathing, not oxygen. Number 2, autonomic nervous system. So it's the nervous system is this next one. Parasympathetic and sympathetic. When the CO2 levels change, they affect the medulla oblongata, which has direct control over your autonomic nervous system. If you start accumulating oxygen look at me. If you start accumulating CO2 and accumulating acid, what's the medulla oblongata going to think? Breathe less or breathe more? Breathe more. Is it going to turn on your fight or flight or your rest and digest response? Fight or flight, right? The sympathetic nervous system is going to start releasing what neurotransmitter? Sympathetic. Fight or flight. Norepinephrine and epinephrine, right? So the epinephrines, the adrenalines. It's going to release those. It's going to do what to your airway? What do you think adrenaline does to your airway? Opens it, right? You have high CO2, it opens the airway, gives you that panicky feeling, right? So you breathe more. You're trying to get it out. If you have barely any CO2 in your brain, it's going to turn down the sympathetic, turn up the parasympathetic, and what's the parasympathetic going to do to your airway? Start constricting it. Okay. This isn't the same as the blood vessels here, because if it were blood vessels, which of these would not be talked about right now? We wouldn't be talking about parasympathetic, right? This is not the same as the blood vessels in this situation. So CO2 and then your autonomic nervous system are the major controllers. Bronchoconstriction. Think about the pathway when you see that. First of all, what's happening to the airway if you're bronchoconstricting? You're squeezing it down. So what would cause bronchoconstriction? High CO2 or low CO2? Low CO2, bronchoconstriction. Think of the pathway. What part of the brain is turned on? Medulla oblongata turns on the what? Bronchoconstriction. Would it be the sympathetic or parasympathetic? Turns on the parasympathetic. What's it do to the sympathetic? Turns it down, right? What happens to this? What's controlling the size? What structures are controlling the size of airways and blood vessels? Smooth muscle. So what's it do to the smooth muscle? Does it contract the smooth muscle or relax it? Hopefully constriction is telling you. If you're a boa constrictor, do you relax to constrict things? No, you contract, right? So you contract the smooth muscle, what's it do to the radius? Decrease the radius, what's it do to the resistance? Increase the resistance, what's it do to the flow? Decrease the flow. When you see that, think of the pathway. Don't just think bronchoconstriction, airway gets smaller. Think of the important parts of it. What has to happen. And then bronchodilation, if all those things cause bronchoconstriction, what do you know is true for bronchodilation? Every one of those things is exactly the opposite. They're all completely the opposite. Another little thing you might want to jot down under here would be the chemicals. What chemical could cause bronchoconstriction? What neurotransmitter? It's not epinephrine. It's acetylcholine. What other chemical associated with allergies would cause bronchoconstriction? Starts with an H. Histamine. So if you wanted to counteract the effects of acetylcholine, like nerve gas that releases a chemical that's like acetylcholine that causes your airways to start constricting, what could you stab that person with? An EpiPen. If they had anaphylactic shock and their airway was starting to squeeze down because of all the histamine in their blood, what could you stab them with? Epinephrine. That's why these concepts are important. If you understand how bronchoconstriction works and somebody's dying because of bronchoconstriction, what do you want to turn up in their body? The sympathetic nervous system. So you need to give them something that's going to turn up their adrenaline fast. All right, what causes the bronchioles to constrict? So if I asked you a question like this, what would cause the bronchioles to constrict? By the way, I would never word a question like this on a test, but where it says increase in carbon dioxide and sympathetics, it means increase carbon dioxide and increase sympathetic. Where it says decrease, it means decrease in carbon dioxide and a decrease in sympathetic. Follow? So when you look at these, which of these would be true? All right, how about number 1? If I increase the CO2, what should happen to my airway? Should constrict, right? So we're half right. So we want to look for something that's increasing CO2. Oh, I'm sorry, what did I just say? I screwed it up already. I'm mentally distracted. An increase in CO2 does what? Causes dilation, right? You want to open it up. So what do we know already? Get rid of increase in CO2. Number 1 and number 2 are out. So we want to decrease carbon dioxide, causes constriction. But what about the sympathetics and parasympathetics? So does decrease in carbon dioxide and a decrease in sympathetics, would that cause bronchoconstriction? Looks like it. What would an increase in sympathetic do? It would cause bronchodilation. Yeah, so number 3 is our right answer. Next one, elastic behavior of the lungs. What's elastic talking about? Snapback. So the technical term for elastic snapback ability is actually elastic recoil. Recoil means to bounce back, right? It's like if you shoot guns, the recoil is when it pushes back against you. It's bouncing back. So elastic recoil is how easily the lungs rebound or snap back after they've been stretched. It's like taking a balloon or a rubber band, stretching out, letting it go, snaps back. That's recoil, elastic recoil. Compliance is how easily it stretches. That's opposing elasticity, right? So compliance is how easily it stretches out. What do you think happens to your lungs as you age? What do you think happens to elasticity? Increase or decrease? Decrease. What do you think happens to compliance? Increase, right? If you look at like people that have emphysema, their chest, they call them barrel chested because they have so much compliance. Their lungs are extremely stretchy. They're like old and saggy, right? They get big and expand out. But their recoil sucks. They've destroyed their elastic recoil so they can't snap it back. What are they better at doing? Getting air in or getting air out? They're good at getting air in. People with emphysema can get lots of air in, but the problem is that they're not getting air out. What is it about the air they're not getting out that's causing problems for them? Carbon dioxide. They can't get it out. So think about this, putting concepts together. If they can't get the carbon dioxide out, the carbon dioxide levels in their blood are going to go up, right? If you have high CO2 in the lungs, you have to have high CO2 in the blood. Why? Because they try and stay at equilibrium. If you have high CO2 in the blood, what else is high in your blood? Acid. So somebody that's had emphysema for years, or chronic emphysema, if you test their blood, what can you safely assume you're going to find? They're in a state of, what do you call it when there's too much acid in their blood? Acidosis. Acidosis. Right. So elastic recoil and compliance. Remember, there's a difference between the two. So the pulmonary elastic behavior is due to high elastic connective tissue, lots and lots of it, helping you snap back, especially when you're young. Unfortunately, when you're a brand new baby, you've got all this really good elastic connective tissue, but man, it's hard to get those muscles working, right? Because you haven't had to use the muscles for breathing before. So elastic would be actually working against you as an infant, or even a premature baby. Bless you. Number 2, alveolar surface tension, and that's the water trying to collapse your lungs, remember? Do you want moisture in your lungs? Heck yeah. You don't want pure water in your lungs. What do you want in your lungs that's full of moisture? Steam. You want that moist, warm air in your lungs to keep it all wet in there, right? To keep it from drying out. You want that, but the problem is that if it starts sticking together and tries to collapse your lungs, then you've got a problem. So that creates surface tension. What's the name of the chemical that eliminates surface tension? Surfactant. What's the name of the cell that gets rid of surface tension by releasing surfactant? Type 2. Yep, type 2 alveolar cells release surfactant. They decrease surface tension, making it easier for you to do what? Collapse your lungs or expand your lungs? Expand. Yep, if you reduce surface tension, you can open your lungs up better. That's why they give surfactant to premature babies, to help them expand their lungs. All right, 2 functions. So surfactant reduces elastic recoil, so the lungs don't collapse, and it also increases pulmonary compliance. So in other words, it doesn't make them snap shut as easy, but it allows them to expand easier. So it reduces work, making the lungs inflate more easily. It's almost like taking the concept is like taking one of those little balloons that are really hard to blow up, and what do you do to make them blow up better? You keep stretching them out, right? Because the more you stretch them out, the more compliant they become, and the less elastic they become. So they're easier and easier to stretch. Right, here's an idea. There's an alveoli. Here's a little water particle or molecule. There's one, there's one, there's one. They're like magnets. Here's the North Pole, there's the South Pole. They attract each other. They're holding onto the wall, so as they come closer together, what are they going to do to that wall? They're going to pull it in. If they start pulling closer to the center, this one starts pulling close to the center, that one starts pulling closer to the center, these two are going to attract each other. What they're trying to do is they're trying to pull all of the walls of the lungs together three-dimensionally. So they're pulling them in to collapse them. Surfactant gets in here and wedges itself between these molecules like a little rubber bumper so that you can't collapse it so easily. So next, the forces keeping the alveoli open. What helps you keep your alveoli open are the transmural gradients. In other words, that pull from the chest, pulling outward, pulling on the pleural cavity. That's a transmural gradient. Pulmonary surfactant, like I just said, helps keep the lungs open, helps them inflate, increases their compliance. And the third one, this is the new one, alveolar interdependence. It means they depend on each other. Alveoli hold hands. They're connected by that little pore of cone that goes in between. So when one alveoli expands, it pulls its neighbor and says, come with me, and it expands too, just like this. Here you have, 7 alveoli? You can see how they're all connected to each other. They all touch each other. If I start pulling on the center one, look what it does to all of its surrounding ones. Well, what are these surrounding ones going to think if that one just starts collapsing on its own? Pull back, right? They're going to pull back. If any of these outer ones start collapsing, what are its neighbors going to think? You can't collapse. We're going to pull together. So they have this interdependence where they're all depending on each other. So as I start collapsing this one, its neighbors will start pulling it and reopening it, helping hold it open. Alveolar interdependence helps keep the lungs open. So those are 3 factors that keep the lungs open. The pull, the transmural gradient, so across the chest wall, across the pleural cavity. Pulmonary surfactant that blocks surface tension. And then the alveoli pulling on each other. All of them are trying to open your lungs. And then 2 things that try and collapse your lungs. Elastic forces, so having too much elastic tissue in there, or even scar tissue that wants to collapse. So people that have something called pulmonary fibrosis, their lungs want to collapse. They can't expand them very well. And then the alveolar surface tension, or that water tension, trying to pull the lungs shut. So 3 things trying to open the lungs, 2 things trying to close the lungs. And they have to balance out overall to keep your lungs suspended. Right, so if I asked you a question like this, what's a force that keeps the lungs closed, or tries to close the lungs? Don't you hate it when you get that song stuck in your head and you just can't get rid of it? I have a song called Axel F from the movie Beverly Hills Cop, and I cannot get that damn thing out of my head. It's driving me nuts. Does anybody know what I'm talking about? Nobody. Wow. Who's old? Google it, or iTunes, whatever you kids do nowadays. YouTube it, right. Axel F is the name of it. Right, so what's the force that keeps the alveoli closed? There's only one of them. Well, there are 2 of them, but only one of them shows up here. What's the one that keeps it closed? That tries to collapse the baby's lungs? The alveolar surface tension. Yep. So the other 3 are trying to open up the lungs. Number 2 is your correct closer. Right. Next, the law of Laplace. You'll never have to calculate this, but you have to get it. You have to understand it. He looked at all the things that try and collapse your lungs. So he looked at the collapsing pressures. He looked at things like surface tension and how much it wants to close. He looked at elasticity, how much it wants to close. And then he looked at other factors that try and open your lungs, right? And he said, in general, what happens is you can look at surface tension, take it times 2, and then divide it by the radius. You'll never have to do this. The big picture is that if you increase the surface tension, what do you do to the collapsing pressure? It's on the top of the equation, so what happens to this? If you forget how this works, it's the same general rule as force divided by pressure, it's force equals pressure divided by resistance. If you take the thing on the top and you double it, what do you have to do to this side of the equation? Double that too. So if I increase the surface tension, what happens to my collapsing pressure? I increase the collapsing pressure. Does it make sense? You put more water in the lungs, they want to do what? Collapse. If I increase the surface tension, they want to collapse. Second is if I take the radius, if I increase the radius, what do I do to this over here? I decrease the collapsing pressure. So in other words, the bigger the alveoli is, does it want to snap shut or does it want to stay open? It wants to stay open. Why is this important? Because if you have a teeny tiny baby alveoli, what's it want to do? You have a tiny small radius, what's it do to the collapsing pressure? Increases the collapsing pressure, wants to snap it shut. If you have the big saggy emphysema alveoli, what's it want to do? Does it want to stay open or collapse? It wants to stay open. It wants to stay open. The problem is you can't get it collapsed and push the CO2 out. So they draw you a little picture like this where it shows the little tiny one versus the big one. Which one's going to collapse first? The little tiny one. It's going to actually force the pressure over to another alveoli. So this one's going to collapse and then you've got big problems. What's this little chemical that's in between here keeping it from collapsing? Surfactant. Yeah, they put the little squiggly tail, kind of like those phospholipids we talked about before. It's actually kind of a lipidy-based chemical that gets in there. Why lipid? Why is the fact that it's a lipid important? Or lipid-like? What's it trying to stop? What's trying to collapse your lungs? Water. It's trying to get in between the water. Remember? Two water molecules, if you put lipid in between them, what do they think of each other? They don't want anything to do with each other because that lipid's in the way. They don't want to go through the lipid to try and get to each other. Like, forget it. I'll go home. Right. And then winding down for today. So the work of breathing normally requires about 3% of your total energy expenditure. So about 3% of the energy that you spend is in breathing. That's for normal, quiet, relaxed breathing like you're doing right there. Here are the things that increase the work of breathing. So if you're wanting to know how can I make my life more miserable, first, if pulmonary compliance is decreased. In other words, if you can't stretch your lungs out, the disease you want to associate with this, pulmonary fibrosis. You have scar tissue around your lungs, around the alveoli. Does scar tissue stretch very well? No, look at any scar. If you pull the tissue around it, the scar stays the same size. It's the skin around it that stretches. So pulmonary fibrosis, you can't stretch the lungs out. When airway resistance is increased, increasing resistance, think of shrinking the radius, increasing the resistance. What disease might this be? Asthma or bronchitis are really good examples, right? Airway resistance is increased. Asthma, they have to work harder to get air. You can see them struggling. Number 3, when elastic recoil is decreased. In other words, their lungs are saggy. They don't snap back anymore. It's like a balloon. The more times you blow the balloon out and let it go, right? Over and over again. What happens to the size of that balloon every time you let it relax? It gets saggier and saggier. It loses its elastic recoil. It's the same as what disease? Where they've been smoking for a long time or working in an environment that damages their lungs, right? So emphysema is what I always go for. I'm going to save COPD for later. Because COPD technically is bronchitis and emphysema combined. So number 3 is emphysema. And number 4, when you do that terrible, nasty exercise thing, that increases the work of breathing. You're going... So in number 1, 2, and 3, when you have any of these 3 diseases, it increases the work put into or the energy needed for breathing from 3% up to roughly 30%. A lot. You ever seen people that have asthma running around the block all excited, full of energy? No, they're like sitting crouching like, oh my god, I can't get air. How about people with emphysema? They don't exactly walk around a lot, right? They do most of their time sitting. Burns a lot of energy just to breathe. when you do that nasty exercise, guess how much energy you use? You go from 3% all the way up to 5%. That's it. So moral of the story is quit smoking, get a little bit of exercise, and take care of your lungs. And that's where we're stopping today. I think that was the last one anyway. Yep, and then in lab we're going to use this, so it was perfect timing, spirometer. The test will be Tuesday. We didn't get as far as we needed to get, so boo, I know, boo. The journal is that neuro thing. We did it already, so it was already due. It came and went. That was the neuro thing that we did back with neuro, where you watched the video and wrote the little journal page. Yeah, that was the extra credit. There will be more extra credit later. Don't sweat it. Sure. Laplace. Yep. Increased surface tension increases collapsing pressure. Decreases surface tension. Right. Yep. Test is Tuesday. Test is Tuesday. Test is Tuesday. Yeah, it's over everything up through respiratory. Well, everything. Everything since the last exam through respiratory. So, muscle, cardiovascular, and respiratory. I think I heard the test is Tuesday.